College Algebra 2.1. Pause it and see if you can figure out the matchstick problem. All right, the correct answer would be to take one from here and make this an 8. I'm trying to remember which one it is. It would be this one right here. So I'm going to take this matchstick out and put it right there. Now I have 9 plus 3 minus 4 equals 8. What we're doing today is going to be intercepts and symmetry. So let's start by intercept. So we're going to graph this function, 8x minus 3y equals negative 18. Now you know how to do this. If we solve for y, we can put this in slope-intercept form, but we're going to do it a different way by intercepts. So I'm going to try to find the x-intercept of this line. To find the x-intercept, we're going to let y equal 0. Because any x-intercept, that's what the y is going to be. So if I let y equal 0, that would make this equation 6x, this essentially becomes all 0, equals negative 18. Divide by 6, and x is negative 3. So the x-intercept is negative 3, so right here. We're going to do the same thing with the y-intercept, except this time we're going to let x equal 0. That would be negative 3y equals negative 18, because if this is 0, this whole thing right here would be 0, so that wipes that part out. If I divide by negative 3, y equals a positive 6. 1, 2, 3, 4, 5, 6, right there. And if I have those two dots, that is enough to graph my line. So that would be right about there. Right there is my line. So graphing intercepts. It is a quick way to get 2 points. A lot of times they give you on the ACT a problem in standard form, and that's a very fast way to get those 2 dots. Symmetry is the other thing we're going to talk about. So here I have this triangle graphed, and we're going to draw the figure so that it's symmetric to these 3 things. Let's start with the x-axis. So for the x-axis, that means I'm flipping it over this line right here. I'm essentially just going to worry about the 3 endpoints, because if I can transfer those 3 endpoints over, then I can draw the triangle. And what I'm going to do is I'm going to count the distance from the x-axis. This is 1 away, so if I go 1 below and put a dot, same thing here, 1 away. And then this one, 1, 2, 3, 4, 5, 6, so 1, 2, 3, 4, 5, 6. And then I essentially have my triangle. Connect those 3 dots. And I have that flipped on the x-axis. All right, we're going to clear that out and do the y-axis now. Same thing, except we're going to count from the y-axis. This is 3 away, so put a dot 3 on the other side. Same thing here. This dot is over here at positive 8, so negative 8 over here. And then once again, I can connect my 3 dots. So there is my y-axis. The origin will be a little bit different. So I'll give you 2 ways to think about this. One way to do the origin is you basically flip it over the x and the y-axis. So I flipped this over the y. Now I'm going to flip that one over the x-axis and put it down here. 1 away, 1 away, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. And there is going to be my triangle. The other way to do that, if you don't want to reflect it twice and make it symmetrical, would be to do this. Let me get a different color going. This point right here is the point 3, 6. Okay, that point ended up landing right here at negative 3, negative 6. So all I have to do is change the sign. This point was at 1, 8. That means I should have a point at negative 1. I'm sorry, not 1, 8. That is at 8, 1. And so I should have a point over here at negative 8, negative 1. So there's a quick way to just transfer it directly over. The other kind of weird way to do it, not sure you're going to want to do it this way, but let me show you, is if I were to draw a line, y equals negative x, and that would be this line right there. I can actually do a weird kind of a count here. Counting the diagonals, let me get a color you can actually see. That is actually 2 diagonals away across the diagonal of the square. So then this is 1 off. You come 1 off over here and count 2. I guess that's not the easiest way to do it, but there is a way to do that using the graph. Just change your signs and you'll have the symmetry down. Testing for symmetry. Okay, so now here's a way to see if something's symmetrical without graphing and counting. So we have 2 ways of doing it. There's a way to test points, and there's a way to test the equation. So here's the x-axis test. To test any point, for example, if I gave you the point 3, 7, if it's reflected over the x-axis, it should be the same x value but the opposite y value. So I can test any point. All I'm seeing, the y value should be the opposite. Now to test the equation, it says replace the y with negative y and it will be equal. So for example, if I were to give you x equals y squared plus 2, if I were to replace that y with negative y, and that essentially doesn't change the equation, in this case it wouldn't, because negative y squared is still going to be a positive y squared, then this would be symmetric with the x-axis. So if it's just a point, it's very easy to tell. If it's the whole equation you're wanting to test, then you're basically seeing if plugging a negative y in for y doesn't make a difference. All right, so all these are going to be very similar. So that was the x-axis. Here's the y-axis. So the y-axis, the front number is changing sign, the x number. And the test for the equation is you replace the x with negative x and no change happens. And then the toughest one is the origin. We kind of already talked about this. Both signs change for a point. For the equation, change x with negative x, y with negative y, and no change happens. So let me show you an example there. If I just give you y equals x, if I were to change both of those to negative, negative y equals negative x, that essentially doesn't make any difference because I can multiply both sides by negative 1 and get back to y equals x. So that didn't make a change. Now, the way this kind of works is you could have all 3 and you could have 1. The one thing you can't have is 2. So you can't have this one work and this one work, but not this one. So it's kind of a weird, you can't have symmetry with 2, but and not the third. So if it's symmetrical with x and symmetrical with y, then it's going to be symmetric with the origin. This is an example where it'd only be the origin. If I replace the y only, it wouldn't work. If I replace the x only, but the origin by itself would work. List the intercepts and tests for symmetry. So here, let's put all this to work here. So for the intercepts, get a pen that's working. Let's go yellow, thin. All right. So the intercepts, I'm going to find the x-intercept, I'm going to let y equals 0. To find the y-intercept, I'm going to let x equals 0. And the test for symmetry, we're going to do the swap out the x, swap out the y, swap out the x and y. So I'm going to pause this, you pause it, try it, and we'll see if we match up. Okay, there are all my answers. Notice I had 2 y-intercepts because we did the square root right here, so don't forget your plus minus. Over here I got the x-axis to work, the y-axis didn't, so I already knew this wasn't going to work, because remember I told you you can't have 2, but we went ahead and tested it, so the only one that works for this does have x-axis symmetry. All right, there's your assignment. Get a good start on it so you can finish in class.